We'll be practicing a few questions pertaining to scheduling. The first question is we have 3 jobs of length j naught equal to 100, j1 equal to 200, and j2 equal to 300. Under SJF scheduling and FIFO scheduling, we want to estimate their turnaround time and response time. So let's look at SJF first. In SJF, we'll have the shortest job running first. So J0 is shorter than J1 is shorter than J2. And let's assume all of them arrive at time t equal to 0. So because we want to execute the shortest job first in SJF, from time 0 till 100, we'll have J0 executing. From 100 till the time J1 completes, just 300, we'll have J1 executing. And from 300 to 600, just for 300 units of J2, we'll have J2 executing. Now for calculating the turnaround time, we look at the time when from the beginning, from the time that the process arrived to the time they were first run. So for response time for J0 is 0 because it came in at 0 and it started executing then. J1 came in at 0 but executed for the first time at t equal to 100. Response time for J1 is 100 and response time for J2 is similarly, it came in at 0 but executed for the first time at t equal to, time equal to 300. The average response time is the sum of all of them divided by 3, so which is 400 by 3 is the average response time. Now if we look at the turnaround time, process J1 came in at 0, completed at 100. So the turnaround time for J0 is 100. Process J1 came in at 0, completed at 300. Turnaround time for J1 is 300. For J2 is came in at 0, completed at 600. So the average turnaround time is the sum all of them divided by 3, which is 1000 divided by 3. Now in the FIFO, if we assume that J0 just arrived marginally before J1, arrived marginally before J2, so FIFO will just execute them in the order of arrival. We'll have the same CPU scheduling as SJF for this particular example. So we'll have the same response time and turnaround time. Okay, so let's look at a different variation of this problem. What if we had the same 3 set of processes, but instead of using SJF or FIFO, we'll use round robin now. So for round robin, as we discussed earlier, so we execute different processes for a time quantum, and then the other processes are executed. So let's say we have J0 equal to 100, J1 equal to 200, and J2 equal to 300 units, and the time quantum is 1 unit. So the way this would execute is from time t equal to 0 till 1, we'll have J1 executing. From 1 to 2, we'll have J0 executing. From time 1 to 2, we'll have J1 executing. And from 2 to 3, we'll have J2 executing. So if we notice, we'll see that we'll have these blocks of 3 processes running together, and they'll run till the time one of the process J1, and J2 gets completed. The shortest one amongst them is J0, which will get completed when it's run for 100 units. So in order to make this process easier, we'll maintain a data structure, let's say, where we capture for different time instances the amount of running time left for J0, J1, and J2. So at time t equal to 0, when all the processes comes, J0 has 100 units left, J1 has 200 units left, J2 has 300 units left. Now, if we continue repeating this process, at time t equal to 300, we'll have another block where at time t equal to 100, we'll have J2 running, J1 running, before that J0 running. So at time t equal to 298, J0 will be consumed. J1 will have run for 99 units, so it will still have 101 units left. And J2 will have run for 99 units, so it will still have 201 units left. At time t equal to 300, which is at this point, J0 is completed, J1 has 100 units left, J2 has 200 units left. Now we still want to run them in round robin fashion, but since J0 is completed, so only J1 and J2 will execute beyond this point of time. So let's look at how they'll execute beyond 300. From 300 to 301, we'll have J1 executing, followed by J2 running from 301 to 302. So now they'll run in blocks of 2, where earlier they were running in blocks of 3. And this will continue till the time J1, which has shorter number of units to consume, is finished. So this will get completed at the time 200 more units from here. So at time 500, we'll have J2, and before that we'll have J1. So J1 would have again would now have consumed these 100 units. It will become 0. And J2 will have also consumed 100 units. It will still have another 100 units left. Now from time 500 to time 600, J2 is the only process which is left. So it will run continuously on the CPU. Now if we look at the various times at which different processes started, and we want to find out the response time. So process J0 started at 0, executed at 0, J1 came in at 0, executed at 1, J2 came in at 0, executed at 2. So the response time, the average response time is 0 plus 1 plus 2 divided by 3, which is 1. And the average turnaround time. So J0 started at 0, it completed at 298. J1 started at 0, it completed at 499. And J2 started at 0, and completed at 600. So that's the turnaround time in this case. Now let's look at the final question. The question is, for what workloads and quantum lengths does SGF deliver the same response time as round robin? So we just had a running example of round robin where we saw that different processes are run consecutively one after another in the time unit. So they each run for a time unit, which is the time quanta of the round robin scheduler. Okay, so again, the question is, for what type of workload and quantum length does SGF deliver the same time as round robin? So the simplest way to solve this is to look at trivial examples. So let's say we have 3 processes of length 10. If we were to schedule them using SJF, so we'll have the CPU trace looking something like the following: J0, J1, J2, where J0, J1, J2 all are of length 10. So the response time in this case is J0 came in at 0, ran for the first time at 0. J1 came in at 0, executed for the first time at 10. J2 came in at 0, executed for the first time at time t20 divided by 3, which is 10. For this trivial case, if we had a round robin scheduling algorithm, let's say we pick up time quantum of 1. So in that case, we'll have J0 running for a single second or unit followed by J1, followed by J2, and this process is repeated. So in this particular case, the response time is 0 plus 1 plus 2 divided by 3, which is 1, which is not equal to 10. So we'll have to increase the quantum to the point such that the response time of a round robin is the same as the SJF algorithm. So if we were to keep, if instead of 1, we had a quantum of 5, we'll have, instead of 1, we'll have it running, J0 will run from 0 to 5, J1 will run from 5 to 10, and J2 will run from 10 to 15. So in that case, the response time will be 0 plus 5 plus 10 divided by 3, which is 15 by 3, which is 5. So if you can carefully notice, the response time for such trivial example is same as the time quantum. So if we were to choose a time quantum Q, we'd have, so if the time quantum is say small q, we'd have process J0 executing from 0 through Q and small q, where let's say Q is less than equal to the length of the process, length of the maximum process.
Are you in a meeting?
I was just recording another. So it runs from Q to 2Q, followed by 2Q to 3Q. From 0 to Q, J0 will run, J1 and J2 will execute. So the response time would be 0 plus Q plus 2Q divided by 3. So Q is less than equal to the length of the processes, all of which are of the same length in this case. It's equal to Q. So if we keep Q equal to 10, that is the quantum equal to the length of the process, we'll have the response time of SJ equal to the response time of round robin. Now let's, for the moment, not bother about the trivial example. Let's take something more complicated. So let's take an example where we have the corresponding lengths as 10, 20 and 30. So for SJF, we'll have the scheduling as follows. J0 runs from 0 to 10. From 10 to 30, we'll have J1. And from 30 to 60, we'll have J2. So the response time is 0 plus 10 for J1 and 30 for J2. The average response time is 0 plus 10 plus 30 divided by 3, which is 40 by 3 for SJF. Now let's look at the same thing for round robin. So if we want to have the same response time, we want to have this exact same schedule, which is possible if we have, so anything, so J0 has to run at least for 10 seconds, J1 has to execute for 20 seconds. Beyond that, J2 will anyway can take up the process, because if J1 is complete, then the processor is left free to be run by J2. So for J1 to run for its full 20 units, we'll want to have the time quantum to be greater than or equal to 20. Now if time quantum is exact 20, we can see how simple the schedule is. If time quantum is greater than 20, so then also J1 will run for only for its 20 units. Beyond that, we'll not have the CPU waiting for, if let's say if TQ was 25 and J1 runs for 20 units, so we'll not have 5 units of CPU go waste. We'll just push J to run at that point of time. So if we're giving, so if we generalize this to n processes arranged in the increasing order of length or according to the SJF order, so we need a time quantum greater than or equal to the n minus 1th job.